Okay, in this last video, we will go through a few templates of how you can write test benches for sequential designs. So this is the first example. You have your time scale, and let's say this test bench is for a 1-bit D flip-flop. So you have your module testbench underscore D flip-flop. Your inputs are of type reg, clock, reset, and data. Output is of type wire, so your Q is a wire. Then you have your integer I. Finally, you have your DFF, which is your unit under test, and then you use your dot notation to tie this design into your test bench. And the first thing, absolute first thing that you should be doing for any system that has a reset is you should reset it before you apply inputs, because you don't know if it carried any previous values from its previous operation. So now, if you don't reset it and if you just start testing it, you can't really validate that your design is working correctly. Okay, so in the initial begin, right, which is this guy to this guy, the first few lines that you see are basically done to reset your system. So you set your clock to 0, your reset to 0. Again, because the reason your clock is 0 and reset is 0 is because we are assuming that the D flip-flop are positive edge triggered D flip-flop, which means that it's only active on the rising edge of my clock, right? So that's why I will start off with setting my clock and reset to 0. And then I'll wait for some period, in this case for two time units. Then I set my reset to 1, and then I set my clock, or I wait for, let's say, another 3 or 5 time units. Then my reset goes to 0, in which I'm waiting for 5 time units. So during this time, what happens is that I use the always construct and generate my clock like this. Okay, so you see that the always block does not have anything in its sensitivity list. So it's an empty sensitivity list, which means this will run forever. Okay, so what this line does is basically it waits for 5 time units, and whatever my previous value of clock was, you see the toggle, so it toggles that value and then it sets that to the new value of clock. So if clock was 0, it becomes 1. If clock was 1, it becomes 0. So that's how this does. And keep in mind that this happens forever. So it's an infinite loop. Okay. So when you're running test benches for sequential designs in Model Sim, you don't hit the run all option because your simulation will run forever. You won't really see any output. You won't see any waveforms. And so you will have to manually go and hit the stop button to stop the simulation. Okay. So inside my initial begin, right, at this point, technically, if you look at the value of your Q, it should be 0, right? At this point, you should have reset your system. Next, you basically run a for loop, right? So my I, which goes from 0 to 1, so I less than 2, which means I goes from 0 to 1. I set the value of my data is equals to I wait for 9 time units, and then I put my display statement, and then I wait for another time unit. So basically you reset and then you apply your stimulus. This is called applying my stimulus. And this line takes care of generating the clock for me, okay? The only thing that you should technically keep in mind, if you didn't observe this already, is you see you have the 9 and a 1. So if you add them up, it becomes a 10, right? So this is, you're waiting for 10 time units inside your for loop. And you see you're waiting for 5 time units before you change your clock. So always you want to wait at least 2 times whatever value you give here. So if your time period is 5 time units, then you want to wait for at least 10 time units. So this is one way of building a test bench. The other way is something like this. Okay. So in this test bench, let's say that you have a 4-bit D flip-flop rather than a 1-bit D flip-flop. Okay. So let's see if I can zoom, focus. Okay, good. So again, so the thing is that I'm assuming that my 4-bit D flip-flop was positive edge triggered and active high reset. Okay, so I have my time scale, module DFF4, all of you familiar with this, my inputs, clock reset, and also my 4-bit 3 down to 0 D and a 3 down to 0 Q. Okay, and my DFF4, which is my unit under test, and then you basically tie the signals together. Again, like before, I take my initial begin and then I reset the system in here. So the Q should now be 0. Technically what I do, I set my reset to 0, clock to 0, I wait for 5 time units. Reset to equals to 1, clock becomes 1, I wait for 5 time units. And then I set my reset to 0 and clock to 0 and wait for 5 time units. So basically, you see that the clock goes from 0 to 1, right? So every time a clock goes from 0 to 1, that guarantees that there is a rising edge of clock in that transition. Okay. you use the always #5 clock equals not clock. So this is used to generate your clock. All of you know this. So the other way is that you monitor the negative edge of your clock, all right? Because my design is working on the positive edge, you monitor the negative edge of the clock, and on the negative edge, you set the value of your data, right? So on the first neg edge of clock, I set the value of data to be zeros. And then you see, I was waiting for 5 time units, my time period is 5, so I wait for 10, okay? So it's just double. You can use that as a small rule of thumb, right? So the idea is that if I set the value of D in this neg edge, in the following pos edge, this value of data is going to be read by my D flip-flop, and I'm going to get my output. And you keep doing that. So you can either put a for loop or as in my case, I've basically just hard-coded those values. You can do either. Well, that concludes this video series for week 1. I hope all of you are safe from the virus, and good luck with your labs.